3 minus is a spectator ion. If you are titrating this with NaOH, and that dissociates into Na plus OH minus, the sodium ions and the nitrate ions are spectator ions, and the net ionic equation is H plus OH minus going to water. And I told you that that was true only for strong acids, that weak acids, because they don't dissociate completely, you can't write them as ionized because they aren't 100% ionized. So one problem people had was recognizing where to break the compounds, and that was true on the ionic double displacement reactions as well. But you are told that this is a weak acid. That means it doesn't dissociate 100%. The second thing that you have to recognize is all of those hydrogens listed first, they're all acidic hydrogens. They are all going to form water with OH. So your product is going to be H2O plus Na, and this has a 3 minus charge. We know that because there are 3 hydrogens. So it's Na3XO4, and this is aqueous, and this is liquid. Okay, so to balance this, we're going to need 3 NaOH, and we're going to make 3 waters. When I do the net ionic equation, I have to write the weak acid as an acid, H3XO4, aqueous, because it doesn't dissociate, plus OH minus, because this does dissociate. And I need 3 of those to form 3 waters, plus XO4, 3 minus, aqueous. So that is your net ionic equation. The only spectator ion in this is the sodium. The only spectator ion, because this species, XO4, 3 minus, is part of a compound on this side, and it's an ion on the other side. We call that a conjugate base. When we do acids and bases in the second semester, we'll talk a lot more about that. But this is the net ionic equation for a weak acid. It's not H plus OH minus yielding water. So that's one. The other issue for a number of you on the net ionic, the other thing on this, as well as, yes, Jonathan?
Nothing, never mind.
Yeah, don't have a question? Okay. The other problem that a number of people had was if you were asked the charge on the ion, and many of you gave me formal charge on X. You were confusing formal charge with charge. The charge on XO4 is 3 minus. I don't need formal charge on the X. I want to know the charge on this entire species. And I know that because there are 3 hydrogens here. Okay. That came up in the ionic equations as well. When you had, let's see, I'll give you one example. You had QNO3 plus Na3XO4. And you were asked, this was a net ionic, and you were asked the charges on Q and the anion here. And it's very clear what you have to recognize. I had some people that were splitting these compounds in strange ways. You have to recognize species you know. You know NO3 minus is a -1, so the Q has to be +1. You know that sodium is +1, and there are 3 of them, So this has to be -3. Now, when you form your compound, you're going to need 3 Qs to balance the charge of an XO4. So this is going to become Q3XO4. And you're going to need, and the other compound is sodium nitrate. And I had a number of people give me Na3NO3, which makes no sense. It's NaNO3 because this has a charge of +1, this has a charge of -1. But to balance it, we need to have a 3 in the front of each of those. That gives us our 3 Qs, and it gives us our 3 nitrates to form the product. So this was a solid, and this was aqueous. So you had some issues with that.
Excuse me?
Question, Chow.
Yeah, I have a question on a weak acids. So why on the reactant you don't split, well, you don't broken down the aqueous?
Because it doesn't. It just doesn't and I said that in class. Weak acids do not ionize to an appreciable degree. They ionize 2-3%, maybe less. So depending upon concentration and depending upon the weak acid. But the difference between a strong acid and a weak acid is strong acids ionize 100%. So we can write them in aqueous solution as ions. Weak acids do not. If they're only roughly 2 to 3% ionized, it doesn't make sense to write them as separate ions because 98% of them exist as molecules in solution. So you have to write it as a molecule. Does that answer your question?
Yes.
Okay.
Professor, I have a question.
Yeah.
For the what's it called, the hydrates question?
Yes.
To get the ratio, don't you like divide the moles of water by the moles of the anhydrous compound? Then that would be
yeah, I have to check that one again. I didn't write that question, and I was checking on some answers, and that's one of the questions that I need to go back and look at the original questions again, because when I do the math, I don't come up with the answers that are listed as the correct answers. So that is a question that I may just simply throw that question out. I don't know yet. I want to go back and go over those questions. But many of you, the mistake that some people made was they calculated moles of they calculated the moles. The molar mass you were given was the molar mass of the anhydrous salt. And many of you use the mass of the hydrated compound. And you can't use that. You have to use the mass after it's heated to calculate the moles of the anhydrous salt. And you use the mass of the hydrated salt minus that to determine the mass of water. Mm-hmm. And then you calculate moles of water. And when I did that on a couple of them, a number of people just made mistakes in how to approach that. And so I couldn't give you credit. But the ones that did it correctly, I looked at it, and a couple of the ones that I looked at, I don't know that the answers there were correct. So I have to go back and check that question. And I may just throw that question out.
Could you show us how to do a problem like that?
Because I know we went over in the lab, but I don't even know.
Yeah, can I do it next time, Diana? Because I want to pull up the question.
Yeah, that's fine.
Okay. And I do want to get on. I do want to go through. I do want to try to finish gas laws today, but I don't think we're going to. I think we'll get through a lot of it. I do want to leave you time for your quiz at the end. It's a quick quiz. It's really not a very long quiz, but I do want to leave you time for that. And I don't think we're going to finish chapter 8 today, but we will finish what I don't finish today. We'll tack on when we start chapter 9, since there's it's only on the final. So we'll have time to do that.
Will the homework still be due Monday then if we don't finish chapter 8?
Say again?
Will the homework still be due on Monday then if we don't?
I can change the homework. I can change the homework date. It's not trivial because I have to change it with Newton as well, but I can do that. So
Okay.
I will do that. No, that's not a concern. Yes.
I'm sorry you're being bombarded with questions, but there's a quiz Tuesday. Could we assume next Tuesday?
Will be on as much as we cover of chapter 8. It will not be any, it will not go any, it won't cover anything we don't cover today.
Okay, thank you.
As I said, I don't mind being considered tough, but I try not to be unfair. Okay. All right, I think we I don't think we did stoichiometry. I don't think we did this slide. But this is, I think we ended with the combined gas laws. Okay, so all this tells you is that we have now got a new way of getting into our stoichiometry equations, and that's using the volume of a gas. If you keep pressure and temperature constant, as long as the gases are at the same pressure and the same temperature, the volume of the gas is going to contain the same number of moles. Remember from Avogadro's law, the volume of the gas is proportional to the number of moles. And since we need to have, in order to do stoichiometry in any equation, we need to have a way of calculating the moles of A and the moles of B. We can do that using volume if we're talking about a gas. Again, they have to be measured at the same temperature and pressure. So it's just a new way into that equation. We can use the ideal gas law to calculate the molar mass. So we don't generally do this anymore. We usually use mass spectrophotometry, but this is a way of measuring the molar mass of an unknown gas. And we can do it this way. We know that the molar mass is determined by taking a mass divided by the number of moles. You are very used to taking the mass, a given mass dividing by a known molar mass to determine how many moles you have of a given compound. So we can take this equation, M divided by molar mass, and substitute it into the ideal gas law. So PV equals nRT becomes PV equals mass divided by molar mass times RT. We can then use algebra to rearrange that equation to solve for molar mass. So molar mass is equal to mass times RT divided by PV. That's just simply an algebraic rearrangement of this equation. But we also know that density equals mass per unit volume. That's the measure of density. So mass divided by volume over here becomes density. So if you can measure the density of a gas multiplied by the ideal gas constant R at a known temperature and pressure, you can determine the molar mass of that gas. You can also use algebra to rearrange that equation. You can use it to calculate molar mass. If you know the molar mass because you know the identity of the gas, you can calculate its density there at a given temperature and pressure, et cetera. So we can rearrange that equation in a number of ways. So it becomes quite useful. Now, the other thing we should know about gases is we talked about the fact that we derived all of those laws without any identity of the gas being known. So it was generally true for all gases, not true for just specific gases. And each gas behaves independently. So each individual gas in a mixture will exert its whatever pressure is appropriate for its number of moles, molecules, etc., and it will exert that in a mixture just as it would if it were in a container by itself. So if we look at three particular gases here, our blue gas is exerting a pressure of 300 kilopascals. The pink one is 600 kilopascals and the yellow one is 450 kilopascals. If we combine all three of these gases into a container of the same volume, they each are exerting their individual pressures, but collectively they have a pressure of the sum of their partial pressures of 1,350 kilopascals. So the total pressure is equal to the sum of the partial pressures of each of those gases individually. And since we know that pressure is equal to nRT over V, that's the rearrangement of the ideal gas law for each of these gases individually, we know that the total pressure is equal to the number of moles of A times RT over V, plus the number of moles of B times RT over V, plus the number of moles of C times RT over V. Or we can simplify that by saying that the total pressure is equal to the sum of the moles of each individual gas times RT over V. So Dalton's law simply says that the total pressure is equal to the sum of the partial pressures. So that's going to introduce a new term called mole fraction. I don't know whether we've introduced this term before, but the mole fraction is chi. Chi, by the way, is one of the few dimensionless quantities in chemistry. It's one of the few numbers that you can write that doesn't have a unit, and that's because it's equal to the mole fraction, or chi of A is equal to the number of moles of A divided by the total moles in the system, and moles divided by moles has no units. For gases then, remember that moles is proportional to the partial pressure. So we can say that the partial pressure of a component A is compared to the total pressure is equal to this rather complex equation, which is just saying the number of moles of A divided by the total moles. So one way of calculating chi is the number of moles of component A. Another way is to calculate the partial pressure of A. So what we're saying here is that the partial pressure of A is equal to the mole fraction of A times the total pressure. And we're saying that chi for a gaseous substance, the mole fraction can be determined by the partial pressure of A divided by the total pressure. So we can use that. One place that we use Dalton's law is when we collect gases over water. When you generate, and I'll walk you through this system here. We have a reaction in this flask that produces a gas. The gas can travel up through this glass tube, and it travels underneath it, because you can imagine if you did this in an open container, the gas would just dissipate. But we can collect it. If this flask here started out filled with water, as that gas bubbles through this tube and bubbles into this container, the gas will displace the water, pushing the water out of the flask, and the gas is collected in this space here. And that allows you to collect the gas separate from the external air. Unfortunately, this gas will contain some water, and that's because while water is generally a liquid, it also exerts a partial pressure. It also, at any given temperature, some of those molecules of water will be vaporized. And the pressure of that water, so this we call this the wet gas because it contains some water. And the total pressure in this system is equal to the sum of the partial pressures, the gas we're collecting plus the water vapor at that given temperature. And the partial pressure of water is very well known. There are tables of it. You can look it up. at given temperatures. There are tables that will give you the partial pressure of water at every 0.2 degrees. This shows you at 1 degree increments, but you can find it written in 0.2 degree increments in tables very easily. And you can determine what the partial pressure of the water is. And the total pressure in this system will generally be atmospheric pressure, whatever atmospheric pressure is. So you can determine the pressure of the gas that's collected by subtracting out the pressure of the water. Note that both gases occupy the same volume, but they do not have the same partial pressure. And the other requirement of this system that's not stated here, but the other requirement of this system is that the gas that you're generating in this flask cannot be one that reacts with water. If it reacts with water, then as it's bubbling through, you're going to be losing some of your gas in a reaction with water. So this is a good way to collect nitrogen gas, for example, because nitrogen doesn't dissolve much in water. To go back to stoichiometry for a moment, Avogadro, this is basically Avogadro's law. If you remember, here's a balanced equation. 3 moles of nitrogen or 3 molecules of nitrogen react with 3 molecules or 3 moles of molecules of hydrogen to form 2 molecules or 2 moles of molecules of ammonia. Because the volume of a gas is a measure of the number of molecules of gas, as long as they're at the same pressure and temperature, we can say that 1 volume of nitrogen will react with 3 volumes of hydrogen to form 2 volumes of ammonia. And that's true because as long as they're at the same temperature and pressure, they will contain the same number of moles. So we can see that in action. If we have a 2-liter sample of ammonia and we can decompose it fully to nitrogen and oxygen in an expandable container, what is the volume of the container under the same conditions of pressure and temperature? There are 2 ways to do that. You can ask the question, how many liters of nitrogen would be formed from 2 liters of ammonia, and determine that based on the molar ratio from the balanced equation, you would get 1 liter of nitrogen. And how many liters of hydrogen would you get from the decomposition of 2 moles of ammonia? It's 3 to 2. You would get 3 liters. So you would total 4 liters of gas. You can do it by treating each gas independently. Or you can do it by saying how many liters of gases would you get from the decomposition of 2 liters of ammonia, recognizing that you get 4 liters of gas. 1 plus 3 is 4. 4 liters of gas to 2 liters of ammonia, and you get the same answer. So you can combine them together either way. But that would be an example of doing a stoichiometry problem based on volumes as opposed to moles. So now we're going to switch gears a little bit, and we're going to talk about a couple of different other properties of gases. One is diffusion. If you smell perfume in a room or cookies when they're baking in an oven, what you're smelling is molecules that are in the gaseous state that are traveling randomly through the air. And that's called diffusion. Those particles will randomly collide with other particles in air, nitrogen, oxygen, carbon dioxide, whatever else is in the air, and disperse as they travel. The mean free path is a measure of the average distance that a molecule can travel between collisions. So before it bumps into a nitrogen molecule or an oxygen molecule. It should be obvious to you that the distance, the mean free path, or the average distance that a molecule can travel will increase the fewer molecules are present. So The fewer the molecules that are present in the air, the farther a molecule can travel before it bumps into something. Typically, the mean free path for any gaseous molecule will be hundreds of times the diameter of the molecule itself. That's because the molecules tend to be pretty small. And we've talked about it before, gases are, air molecules are spread apart, and in between them is mostly empty space. And we'll talk more about that in a minute. So where do we see this? We see this when gases are mixed. So if you have a system like this, where you have two containers, this container has oxygen, this container has all hydrogen, and it's separated by a stopcock, which closes off the two containers. If you open this stopcock and allow the molecules to move freely, they will move freely until over time, you will find that the molecules will be randomly dispersed between the two systems, and you'll have an equal mixture on both sides of hydrogen and oxygen. We're going to talk more about that in second semester. The system is actually lower energy in this form when the molecules are randomly mixed than they are in this form where they're separated by type. That lower energy is actually directed by probability. There are many more probabilities of having the molecules dispersed randomly than there is having them arranged like this. You think of it as like a deck of cards. If you took a deck of cards and lined the cards up in order, ace through king, each of the four suits separated, there's only one way that can be done, where each suit is lined up in order. Once you've shuffled that deck, you have a random distribution of cards, and there are hundreds of thousands of ways that those cards could be randomly organized, whereas there's only one way they can be perfectly organized. So that probability is much greater that the cards will be distributed randomly. And it's the same idea. We'll go into that more when we talk about energy. So effusion is another property, but effusion is a little bit different than diffusion. Diffusion is when you have molecules randomly moving around in a container, bumping off of each other. Effusion is similar, but it requires that the molecules move through a tiny hole. So we have two chambers here with a tiny hole in between, and the molecules move from this side of the container into this side of the container one at a time. The hole is very, very small. It's much smaller than the mean free path. And you can measure the rate at which these molecules actually move through that hole into the other side of the container. And Graham empirically determined that the smaller the molecule, the more rapidly they would effuse, the more rapidly they would move into this second container. We can state that as Graham's law of effusion. The rate of effusion is proportional, that's what that symbol means, is proportional to the inverse of the square root of the molar mass. So the heavier the particle, the slower the rate of effusion. And that kind of makes sense. If you think of a heavier particle, it's lumbering around, it's moving more slowly. What's required for it to go effuse through this tiny hole is that it travel in the right direction and collide right at that hole and find its way through. And the slower moving particles, that's going to happen much less often. So we can use a chamber like this, and we can compare the effusion rates of two different molecules, of effusion rate of A to the effusion rate of B. Each of these is going to be proportional to 1 over their molar mass. So if we compare the ratio of the rate of effusion A, of molecule A, to the rate of effusion to molecule B, we end up with this equation. And if you know the identity of one of these gases, you measure the rates of effusion and you can calculate from that the molar mass of the second gas by comparing them in this equation. So it's a very simple mathematical process. You have to know the identity of one of these gases and you measure the rates of effusion of both of them. They have to be measured at the same temperature in the same chamber in order for that to work. So let's talk about kinetic molecular theory. Most of the material that we've talked about so far was all determined empirically, just by studying them, taking gases and looking at how they behave when you increase temperature, when you increase pressure, when you change the volume, etc. So all of these were gathered together into something called kinetic molecular theory, or KMT. And this is the theory that we have on gases. The first postulate is that gases are composed of molecules that are in continuous, rapid, random motion. They are always traveling in straight lines, and they change direction only when they collide either with another molecule or with the wall of the container. So they just are in constant random motion. The second postulate says that molecules of the gas are negligibly small compared to the distance between them. That's another way of saying what I stated before. Gases are mostly empty space. The size of the molecules is very small compared to the volume of the container. Another way of saying that, you might have in high school chemistry, they may have told you that the volume of the particles is essentially zero compared to the volume of the container. The third postulate is that the pressure of the gas is exerted by the molecules bumping against the walls of the container. So literally the walls making the molecules making collisions on the walls of the container is what is recorded as the pressure of that gas. The fourth postulate is that gas molecules do not interact with each other. They don't have any attractive or repulsive forces acting on each other or on the walls of the container, so that their collisions are perfectly elastic. That means if two molecules collide, they bump off of each other without any loss of energy. Now, they may transfer, if their energy is measured in kinetic energy, they may transfer energy from one molecule to another, but they don't lose any energy. So they're perfectly elastic collisions. And the final postulate is that the average kinetic energy of a gas is proportional to its temperature in Kelvin. So KE average, or average kinetic energy of the gas, is equal to some constant times its temperature in Kelvin. This is why we need to have temperature. When we're doing gas laws, we have to have temperature in Kelvin. So let's look at how kinetic molecular theory explains the gas laws that we've talked about. So we'll talk about Gay-Lussac's law. Remember that in Gay-Lussac's law, we had pressure and temperature changing, but volume was constant and the number of moles of gas were constant. So if this is our baseline and we increase the heat, we said that the average kinetic energy was proportional to temperature. As the temperature increases, those molecules are going to start moving faster. If we haven't changed the volume of the container, that means they're going to travel faster and hit the walls of the container more often, and the pressure that is recorded is going to increase. Since pressure is a measure of collisions, and collisions increase, the pressure increases. How about Boyle's law? Remember, Boyle's law is P1 V1 equals P2 V2. So here is our baseline situation where we have a certain amount of gas, moles and temperature are constant, but we've changed the volume. We pushed down on this piston and we've reduced the volume. In this case, with volume decreased, even though the molecules aren't moving any faster, they have a lot shorter distance to travel. So they are going to increase collisions with the wall of the container because they're have less distance to travel. So as volume decreases, the pressure increases. So Boyle's law can be explained from kinetic molecular theory. What about Avogadro's law? Well, in Avogadro's law, we're talking about volume and number of moles varying, pressure and temperature are constant. So here is our baseline. We've added moles to this. If pressure is going to be constant, since we have more molecules in here, they would create a higher pressure unless you increase the volume of the gas. Once you've increased the volume of the gas and given these molecules a longer distance to travel, that is how you keep the pressure constant. So the volume has to increase if pressure is to remain constant for this gas. So we can explain all of the gas laws based on kinetic molecular theory. So let's talk a little bit about molecular velocities. We talk about average kinetic energy. Not all particles of a gas in a sample will move at exactly the same speed. Some of them will be moving faster, some of them will be moving slower. That's why we talk about the average kinetic energy and average speeds. So what you get when you measure the speeds of all of the individual particles in a gas, you end up getting a curve that looks like this. It's called a Maxwell-Boltzmann distribution. The most probable speed is here. V sub p is the most probable speed. It's where the peak is the highest. The root mean square speed is something a little bit different. What you do is you square all of the velocities of all of the particles, add them together, divide them by the number of moles of particles, and then take the square root. You might ask, why do we square them and then take the square root? If you remember that velocity is a vector quantity, you will have some particles moving in a positive x direction, some particles moving in a negative x direction. If you were...
Sorry, Professor.
Yes.
Could you explain that equation? I know it was really simple, but can you just say that one more time? I'm just trying to keep up.
So root mean square speed, RMS means root mean square speed. And the way we calculate it, this is what it reduces to. What we do is we take the speed of every individual particle in the sample and square it, and then divide it by the number of particles in the sample to get the average speed of the particles in the sample. That's what root mean square speed means, the average speed. What I was saying now is you could ask, why did you bother to square it first and then take the square root? And what I can say is that velocity is a vector quantity. You will, if you have a particle moving in the positive x direction and a particle moving in the negative x direction, if you add it, even if they have this, if they have the same velocity and you add those velocities together, you end up with 0, which makes no sense. So by squaring the velocities first, you are eliminating the negative sign. You are eliminating the direction from the velocity, whether it's in a positive direction or a negative direction. You're eliminating that but then you have to take the square root to get to the actual velocity. Does that make sense for everybody? You square it to get rid of the vector nature of that quantity, and then divide by the number of particles. And that gives you the average velocity in that sample, but we call it the root mean square speed because we square it first.
Professor?
Yes.
So the U is velocity?
Yes, it really means
Okay.
it's the root mean square speed, and it really it's a measure of the velocity, but it's we don't call it velocity because velocity is a vector quantity, and we've eliminated the vector nature. Remember, vectors have magnitude and direction, and by squaring it and then taking the square root, we've gotten rid of the direction part of it and gotten back to just the speed.
How would we get the number of molecules?
You can't. I mean, you're talking if you're talking about even a tenth of a mole, think of what a mole is. It's you're not going to be asked to do this. I mean, if you were asked to do that, we would be asking you to do it for a sample of 4 particles or a finite number of particles. Typical samples of gas, you can't do that. There's too many particles in the sample. But you would divide it by the number of moles. N is just the number of moles. Okay, so the average kinetic energy of a mole of gas is equivalent to Ke average is 1/2 times the molar mass times the root mean square speed. But we also know that it's proportional to temperature in Kelvin. So we have these two equations, both of which measure the average kinetic energy. So we can combine them to end up with an equation that says root mean square speed is equal to 3RT divided by the molar mass, and we take the square root of that quantity, and that's how you get the root mean square speed. So you're not going to be adding these for individual particles. You can measure the temperature of a gas. R is the gas constant. If you know the molar mass of the gas, you can calculate the root mean square speed of that gas at any given temperature. And I'm not going to have you do it now, but this is posted, so you can certainly practice that by verifying that the root mean square speed for 1 mole of oxygen at minus 23 degrees Celsius is 441 meters per second. So that would be a chance for you to practice. It's a very simple equation.
Professor?
Yes.
Would the R there be 0.0826?
Well, molar mass is in grams per mole. You have to think about what you need to calculate to cancel. Molar mass is grams per mole. Remember that your root mean square speed is meters per second. So we have to end up in meters per second. So this liter atmospheres per mole Kelvin isn't going to work here. You're going to have to use 8.314. Mm-hmm. Because that gives you the correct units to cancel. Temperature is in Kelvin. 8.314 is joules per mole Kelvin. And given what a joule is, you end up canceling appropriately. So you need 8.314.
Okay.
So real quick, you said the R is the gas constant?
That is the gas constant with those units. That's one of the values of the gas constant. 8.314 joules per mole Kelvin. Let's see. Whoops. I'm sorry. I didn't mean to do that. I meant to do this.
I'm sorry if this was already asked, but when we're given questions, is it up to us to determine which constant to use, or is it go to us?
I'm not going to tell you.
Okay. All right.
Yep. You're in college now. Got to figure that out. Hey, my high school kids had to figure that out. Okay. So velocity distribution and temperature. We said that the average kinetic energy is proportional to temperature. So the velocity is going to change with temperature. And so we can look at a curve. When the temperature of a gas increases, both the peak of the curve changes and the root mean square speed. So this is a measure of nitrogen at different temperatures, and you can see that as the temperature increases, the most common velocity or most probable velocity is going to shift to higher temperatures. That kind of makes sense. The curve, however, the area under the curve has to stay the same. So that means that as this distribution becomes broader, the peak has to come down. So at lower temperatures, you have a much higher peak and a much narrower curve. As the temperature increases, the peak shifts to the right and the height of the peak comes down, and the area stays the same, but the curve broadens. So you end up getting a variation of the curve that looks something like this. This is all nitrogen at different temperatures. When you look at the mass, this would be all measured at the same temperature, but we're measuring different gases. This is measuring different noble gases, all at the same temperature. Heavier molecules have a smaller peak and a lower root mean square. They are speed. They are moving more slowly. However, the population doesn't change. So these would be the measures of all the same amount of gas, but at the same temperature, but the peak changes. So the heavier molecule is going to have a much narrower range. The lighter molecule, helium down here, has a much broader curve and a lower peak to a lower probable velocity. So the area under the curve has to stay the same because you're talking about the same amount of gas, but the shape of the curve will change. So the question is kinetic energy average the same for all molecules? The answer is yes, it is. At the same temperature, average kinetic energy is going to be the same for all of these molecules. So we can use KMT and root mean square speed to explain Graham's law. And this is just the equation that we derived for root mean square speed before. And this is Graham's law. Rate of effusion is proportional to root mean square speed. When we compare gas A to gas B, we end up plugging in 3 RT over molar mass for root mean square, and we end up just verifying Graham's law of effusion using KMT. So this is a way of matching our theory to explain gas behavior to the empirical things that we observe for that gas. I think, yes, I believe that we are at okay, 1, 2, 3. These last slides are those last slides are all practice problems. So we have only a few more to go through, and I think we can do this fairly quickly. We have assumed that we've made 2 assumptions. There were 2 assumptions that we made in the kinetic molecular theory that are actually not true. One of those is that gases do not attract or repel each other. Gas molecules do can attract and repel or repel each other. So it is true that if gases will not interact with each other if they can't find each other, if they are very far apart, or if they're moving so quickly that they don't have time to interact with each other. So if we think about that, we can say that, I'm sorry, I didn't need to do that. I wanted to get my pen. We can say that at low temperature, the molecules are moving so slowly that they have more time to interact with each other. And so they will have more of an interaction at low temperatures when they're moving slowly. The other time that they will behave non-ideally, and that's at high pressure, we can say that there are many more gas particles present. So if there's more chance of interaction with another particle at high pressure, they are less likely to behave ideally. So at very low pressures, and I want you to look at this, what we're measuring here is the compressibility, Z of a gas, and we're measuring it and comparing it to the pressure of the gas. And I want you to pay attention to the scale. We're looking at several individual gases, but what we're saying for an ideal gas, it should be along this line of 1. The compressibility compared to pressure should equal 1 for an ideal gas. And if you look at the scale of pressures, we're talking 200 atmospheres, 400 atmospheres. So if you're talking down around 1 atmosphere pressure, you're talking right down here at the beginning of this scale. And all of these gases are pretty close to 1. So they do behave ideally at low pressures, and 1 atmosphere pressure or lower is low enough for most of those gases to behave ideally. So at high pressure and low temperature, is when you will see them behaving less ideally. So when we talk about pressure, another thing that we talked about was the other concept we talked about was the volume of the gas particles themselves. One of the things we said was that in comparison to the volume of the gas, the volume of the particles themselves is negligible or near zero. And gases are matter. Our definition of matter is that it has mass and occupies space. So the volume of the particles is not zero. It is small compared to the container, but it is not zero. So at low pressure, the volume of the gas particles is insignificant. That low pressure means that we have very few particles compared to the volume of our container. And so we can say that they have almost no volume. At high pressure, the volume of the gas particles is not insignificant. The available volume in which the molecules have to move is reduced. If you think about it this way, a molecule of a gas can occupy any space in that container except where another gas molecule is. They can't occupy the same space. So if you have high pressure and a lot of gas molecules there, then the volume of space available to any given particle is going to be reduced. So gas molecules will behave more ideally at low pressure and high temperature when they can't interact so much with each other. And as we said, at low temperatures, gases do not behave ideally because the intermolecular forces become significant. They interact with each other. So the two concepts that we made, the two assumptions we made in kinetic molecular theory was that the gas particles had essentially zero volume when compared to the container, and they had no interactions with each other. That is only true under certain conditions. It is not the way real gases behave. Under normal pressure conditions that we would measure gases, however, it is pretty true. They will behave pretty ideally at those low pressures and high temperatures. They will tend to behave pretty ideally. So I think that's it. We can talk about the van der Waals equation next time, and the rest of those are practice problems. So we will stop sharing. Any questions before I send you to do your quiz?
Professor?
Yes.
So ideal means when they interact, right? The word ideal.
Most of the time you will be asked to treat gases like ideal gases. It is the assumption that you're going to make in solving any gas law problem is that they are going to behave ideally. We'll talk about the van der Waals equation. Van der Waals spent a lot of time looking at gases and understanding how PV equals nRT, which is the ideal gas equation, changes for real gases. How do you change PV equals nRT to take into account that gas molecules do have volume and they do interact with each other? That is basically what van der Waals did. For the most part, under the pressures that you are dealing with, and the temperatures that you'll be dealing with, you can ignore van der Waals equation. You can ignore the volume of the particles. You can ignore their interactions. Understanding the fact that real gases will deviate some it's important to know that they will deviate some, and when they'll deviate some, it's also important for you to understand why they deviate from ideal behavior. In other words, one of the things I want you as scientists to always remember is what were the assumptions we made when we developed that theory? And how valid are those assumptions? In general, under normal circumstances, they're pretty valid. And you can treat gases as ideal gases. It's not important to me that you're able to calculate the actual pressure based on van der Waals equation or anything like that. What's more important for me is that you understand why gases might deviate from ideal behavior.
Okay, thank you.
But I have a question.
Sure.
But we do also need to know how it's happened, and then like we need to know all the equation and stuff for the test.
We'll talk more about that next time. It's not on today's quiz, but I'll talk about that more next time. We'll finish up. It will only take us 10 minutes to finish up on this next time, and then we'll start chapter 9.
Okay.
There are
Great.
problems for you to practice on this PowerPoint, so you can certainly do those as practice. But for now, I think you guys want to get to your quiz. I assume. Yes?
Yeah,
Any other
Professor,
questions?
one last thing.
Yeah, sure.
Can you post the right answers the way you did the other time for the
Sure, the problems on the
questions?
PowerPoint?
Yeah.
Sure, we'll do.
All right. Thanks.
Okay. Head to your quiz. It's available. It should only take you about 10 minutes, I think. I think you're allowed 15, but it should only take you about 10.
Professor, do you want units of liters or milliliters?
It doesn't matter. If it's, I'll check them all, and if I don't remember what the units were that I required, but
Okay.